is that the underlying embedding algorithm might require non-trivial compute and time to run. Before we move on to discuss AI as a judge, let's go over a quick introduction to embedding. The concept of embedding lies at the heart of semantic similarity, and is the backbone of many topics we explore throughout the book, including vector search in Chapter 6 and data deduplication in Chapter 8. Exact evaluation, 133. 13. While a 10,000 element vector space seems high-dimensional, it's much lower than the dimensionality of the raw data. An embedding is, therefore, considered a representation of complex data in a lower dimensional space. 14. There are also models that generate word embeddings, as opposed to documentation embeddings, such as Word2Vec, Mikhailov et al., Efficient Estimation of Word Representations in Vector Space, AR14, V3, September 7, 2013, and Glove, Pennington et al., Glove, Global Vectors for Word Representation, the Stanford University Natural Language Processing Group, blog, 2014. Introduction to embedding. Since computers work with numbers, a model needs to convert its input into numerical representations that computers can process. An embedding is a numerical representation that aims to capture the meaning of the original data. An embedding is a vector. For example, the sentence, "The cat sits on a mat," might be represented using an embedding vector that looks like this: 0, 11, 0, 02, 0, 54. Here, I use a small vector as an example. In reality, the size of an embedding vector, the number of elements in the embedding vector, is typically between 100 and 10,000. 13 models trained especially to produce embeddings include the open-source models BERT, CLIP, contrastive language image pre-training, and sentence transformers. There are also proprietary embedding models provided as APIs. 14. Table 3.2 shows the embedding sizes of some popular models. Table 3.2. Embedding sizes used by common models. Model embedding size: Google's BERT base, 768 BERT large, 1024 OpenAI's CLIP image, 512 text, 512 OpenAI embeddings API text embedding 3 small, 1536 text embedding 3 large, 3072 Coheres embed v3 embed English v3. 0, 1024 embed English Lite 3. 0, 384 Because models typically require their inputs to first be transformed into vector representations, many ML models, including GPTs and llamas, also involve a step to generate embeddings. Transformer architecture on page 58 visualizes the embedding layer in a transformer model. If you have access to the intermediate layers of these models, you can use them to extract embeddings. However, the quality of these embeddings might not be as good as the embeddings generated by specialized embedding models. 134, Chapter 3, Evaluation Methodology. The goal of the embedding algorithm is to produce embeddings that capture the essence of the original data. How do we verify that? The embedding vector, 0, 11, 0, 02, 0, 54, looks nothing like the original text, "The cat sits on a mat." At a high level, an embedding algorithm is considered good if more similar texts have closer embeddings, measured by cosine similarity or related metrics. The embedding of the sentence, "The cat sits on a mat," should be closer to the embedding of "The dog plays on the grass" than the embedding of "AI research is super fun." You can also evaluate the quality of embeddings based on their utility for your task. Embeddings are used in many tasks, including classification, topic modeling, recombiner systems, and RAG. An example of benchmarks that measure embedding quality on multiple tasks is MTEB, Massive Text Embedding Benchmark, Munigoff et al., 2023. I use text as examples, but any data can have embedding representations. For example, e-commerce solutions like Criteo and Coveo have embeddings for products. Pinterest has embeddings for images, graphs, queries, and even users. A new frontier is to create joint embeddings for data of different modalities. CLIP, Radford et al., 2021, was one of the first major models that could map data of different modalities, text and images, into a joint embedding space. ULEP, Unified Representation of Language, Images, and point clouds, Shui et al., 2022, aims to create unified representations of text, images, and 3D point clouds. ImageBind, Gerthar et al., 2023, learns a joint embedding across 6 different modalities, including text, images, and audio. Figure 3.6 visualizes CLIP's architecture. CLIP is trained using image, text, pairs. The text corresponding to an image can be the caption or a comment associated with this image. For each image, text, pair, CLIP uses a text encoder to convert the text to a text embedding, and an image encoder to convert the image to an image embedding. It then projects both these embeddings into a joint embedding space. The train-ing goal is to get the embedding of an image close to the embedding of the corresponding text in this joint space. Exact evaluation 135. 15. The term AI judge is not to be confused with the use case where AI is used as a judge in court. Figure 3.6. CLIP's architecture, Radford et al., 2021. A joint embedding space that can represent data of different modalities is a multimodal embedding space. In a text-image joint embedding space, the embedding of an image of a man fishing should be closer to the embedding of the text a fisherman than the embedding of the text fashion show. This joint embedding space allows embeddings of different modalities to be compared and combined. For example, this enables text-based image search. Given a text, it helps you find images closest to this text. AI as a judge. The challenges of evaluating open-ended responses have led many teams to fall back on human evaluation. As AI has successfully been used to automate many challenging tasks, can AI automate evaluation as well? The approach of using AI to evaluate AI is called AI as a judge or LLM as a judge. An AI model that is used to evaluate other AI models is called an AI judge. 15136, Chapter 3, Evaluation Methodology. 16. In 2017, I presented at a NeurIPS workshop MEWR, Machine Translation Evaluation Metric Without Reference Text, an evaluation method that leverages stronger language models to automatically evaluate machine translations. Sadly, I never pursued this line of research because life got in the way. While the idea of using AI to automate evaluation has been around for a long time, 16 it only became practical when AI models became capable of doing so, which was around 2020 with the release of GPT-3. As of this writing, AI as a judge has become one of the most, if not the most, common methods for evaluating AI models in production. Most demos of AI evaluation startups I saw in 2023 and 2024 leveraged AI as a judge in one way or another. LangChain's State of AI report in 2023 noted that 58% of evaluations on their platform were done by AI judges. AI as a judge is also an active area of research. Why AI as a judge? AI judges are fast, easy to use, and relatively cheap compared to human evaluators. They can also work without reference data, which means they can be used in product-tie-in environments where there is no reference data. You can ask AI models to judge an output based on any criteria: correctness, repetitiveness, toxicity, wholesomeness, hallucinations, and more. This is similar to how you can ask a person to give their opinion about anything. You might think, but you can't always trust people's opinions. That's true, and you can't always trust AI's judgments, either. However, as each AI model is an aggregation of the masses, it's possible for AI models to make judgments representative of the masses. With the right prompt for the right model, you can get reasonably good judgments on a wide range of topics. Studies have shown that certain AI judges are strongly correlated to human evaluators. In 2023, Xing et al. Found that on their evaluation benchmark, MT-Bench, the agreement between GPT-4 and humans reached 85%, which is even higher than the agreement among humans, 81%. Alpaca Eval authors, Du Bois et al., 2023, also found that their AI judges have a near-perfect, 0.98, correlation with LMSYS's Chat Arena leaderboard, which is evaluated by humans. Not only can AI evaluate a response, but it can also explain its decision, which can be especially useful when you want to audit your evaluation results. Figure 3.7 shows an example of GPT-4 explaining its judgment. Its flexibility makes AI as a judge useful for a wide range of applications, and for some applications, it's the only automatic evaluation option. Even when AI judgments aren't as good as human judgments, they might still be good enough to guide an application's development and provide sufficient confidence to get a project off the ground. AI as a judge 137. Figure 3.7. Not only can AI judges score, they also can explain their decisions. How to use AI as a judge? There are many ways you can use AI to make judgments. For example, you can use AI to evaluate the quality of a response by itself, compare that response to reference data, or compare that response to another response. Here are naive example prompts for these three approaches. 1. Evaluate the quality of a response by itself. Given the original question, given the following question and answer, evaluate how good the answer is for the question. Use the score from 1 to 5. 1 means very bad. 5 means very good. Question, answer, score 138, Chapter 3, Evaluation Methodology. Compare a generated response to a reference response to evaluate whether the generated response is the same as the reference response. This can be an alternative approach to human-designed similarity measurements. Given the following question, reference answer, and generated answer, evaluate whether this generated answer is the same as the reference answer. Output true or false. Question, reference answer, generated answer, 3. Compare two generated responses and determine which one is better or predict which one users will likely prefer. This is helpful for generating preference data for post-training alignment, discussed in Chapter 2, Test Time Compute, discussed in Chapter 2, and ranking models using comparative evaluation, discussed in the next section. Given the following question and 2 answers, evaluate which answer is better. Output A or B. Question, A, first answer, B, second answer. The better answer is, a general-purpose AI judge can be asked to evaluate a response based on any criteria. If you're building a role-playing chatbot, you might want to evaluate if a chatbot's response is consistent with the role users wanted to play, such as, does this response sound like something Gandalf would say? If you're building an application to generate promotional product photos, you might want to ask, from 1 to 5, how would you rate the trustworthiness of the product in this image? Table 3.3 shows common built-in AI as a judge criteria offered by some AI tools. Table 3.3. Examples of built-in AI as a judge criteria offered by some AI tools, as of September 2024. Note that as these tools evolve, these built-in criteria will change. AI tools built-in criteria: Azure AI Studio groundedness, relevance, coherence, fluency, similarity, MFlow. Metrics: faithfulness, relevance, LangChain criteria, evaluation, conciseness, relevance, correctness, coherence, harmfulness, maliciousness, helpfulness, controversiality, misogyny, insensitivity, criminality. Ragas: faithfulness, answer, relevance. It's essential to remember that AI as a judge criteria aren't standardized. Azure AI Studio's relevance scores might be very different from MFlow's relevance scores. These scores depend on the judge's underlying model and prompt. AI as a judge 139. How to prompt an AI judge is similar to how to prompt any AI application. In general, a judge's prompt should clearly explain the following. 1. The task the model is to perform, such as to evaluate the relevance between a generated answer and the question. 2. The criteria the model should follow to evaluate, such as your primary focus should be on determining whether the generated answer contains sufficient information to address the given question according to the ground truth answer. The more detailed the instruction, the better. 3. The scoring system, which can be one of these, classification, such as good/bad or relevant/irrelevant/neutral. Discrete numerical values, such as 1 to 5. Discrete numerical values can be considered a special case of classification, where each class has a numerical interpretation instead of a semantic interpretation. Continuous numerical values, such as between 0 and 1, e.g., when you want to evaluate the degree of similarity. Language models are generally better with text than with numbers. It's been reported that AI judges work better with classification than with numerical scoring systems. For numerical scoring systems, discrete scoring seems to work better than continuous scoring. Empirically, the wider the range for discrete scoring, the worse the model seems to get. Typical discrete scoring systems are between 1 and 5. Prompts with examples have been shown to perform better. If you use a scoring system between 1 and 5, include examples of what a response with a score of 1, 2, 3, 4, or 5 looks like, and if possible, why a response receives a certain score. Best practices for prompting are discussed in Chapter 5. Here's part of the prompt used for the criteria relevance by Azure AI Studio. It explains the task, the criteria, the scoring system, an example of an input with a low score, and a justification for why this input has a low score. Part of the prompt was removed for brevity. Your task is to score the relevance between a generated answer and the question based on the ground truth answer in the range between 1 and 5, and please also provide the scoring reason. Your primary focus should be on determining whether the generated answer contains sufficient information to address the given question according to the ground truth answer. 140, Chapter 3, Evaluation Methodology. If the generated answer contradicts the ground truth answer, it will receive a low score of 1 to 2. For example, for the question "Is the sky blue?" the ground truth answer is yes, the sky is blue, and the generated answer is no, the sky is not blue. In this example, the generated answer contradicts the ground truth answer by stating that the sky is not blue, when in fact it is blue. This inconsistency would result in a low score of 1 to 2, and the reason for the low score would reflect the contradiction between the generated answer and the ground truth answer. Figure 3.8 shows an example of an AI judge that evaluates the quality of an answer when given the question. Figure 3.8. An example of an AI judge that evaluates the quality of an answer given a question. An AI judge is not just a model, it's a system that includes both a model and a prompt. Altering the model, the prompt, or the model's sampling parameters results in a different judge. Limitations of AI as a judge. Despite the many advantages of AI as a judge, many teams are hesitant to adopt this approach. Using AI to evaluate AI seems tautological. The probabilistic nature of AI makes it seem too unreliable to act as an evaluator. AI judges can potentially introduce non-trivial costs and latency to an application. Given these limitations, some teams see AI as a judge as a fallback option when they don't have any other way of evaluating their systems, especially in production. AI as a judge. 141. Inconsistency. For an evaluation method to be trustworthy, its results should be consistent. Yet AI judges, like all AI applications, are probabilistic. The same judge, on the same input, can output different scores if prompted differently. Even the same judge, prompted with the same instruction, can output different scores if run twice. This inconsistency makes it hard to reproduce or trust evaluation results. It's possible to get an AI judge to be more consistent. Chapter 2 discusses how to do so with sampling variables. Xing et al. 2023 showed that including evaluation examples in the prompt can increase the consistency of GPT-4 from 65% to 77.5%. However, they acknowledged that high consistency may not imply high accuracy. The judge might consistently make the same mistakes. On top of that, including more examples makes prompts longer, and longer prompts mean higher inference costs. In Xing et al. S experiment, including more examples in their prompts caused their GPT-4 spending to quadruple. Criteria ambiguity. Unlike many human-designed metrics, AI as a judge metrics aren't standardized, making it easy to misinterpret and misuse them. As of this writing, the open-source tools MFlow, Ragas, and LlamaIndex all have the built-in criterion faithfulness to measure how faithful a generated output is to the given context, but their instructions and scoring systems are all different. As shown in Table 3.4, MFlow uses a scoring system from 1 to 5, Ragas uses 0 and 1, whereas LlamaIndex's prompt asks the judge to output yes and no. Table 3, 4. Different tools can have very difficult default prompts for the same criteria. Tool prompt, partially omitted for brevity. Scoring system mflow faithfulness is only evaluated with the provided output and provided context. Please ignore the provided input entirely when scoring faithfulness. Faithfulness assesses how much of the provided output is factually consistent with the provided context. Faithfulness. Below are the details for different scores. Score 1. None of the claims in the output can be inferred from the provided context. Score 2. 1 to 5 ROG. Your task is to judge the faithfulness of a series of statements based on a given context. For each statement you must return verdict as 1 if the statement can be verified based on the context or 0 if the statement cannot be verified based on the context. 0 and 1. 142, Chapter 3, Evaluation Methodology. Tool prompt, partially omitted for brevity. Scoring system llama index. Please tell if a given piece of information is supported by the context. You need to answer with either yes or no. Answer yes if any of the context supports the information, even if most of the context is unrelated. Some examples are provided below. Information: apple pie is generally double-crusted. Context: an apple pie is a fruit pie. It is generally double-crusted, with pastry both above and below the filling. Answer: yes, yes, and no. The faithfulness scores outputted by these three tools won't be comparable. If, given A, context, answer, pair, mflow gives a faithfulness score of 3, ROGA's outputs 1, and llama index outputs no, which score would... Imagine that last month, your application's coherence score was 90%, and this month, this score is 92%. Does this mean that your application's coherence has improved? It's hard to answer this question unless you know for sure that the AI judges used in both cases are exactly the same. What if the judge's prompt this month is different from the one last month? Maybe you switched to a slightly better performing prompt, or a coworker fixed a typo in last month's prompt, and the judge this month is more lenient. This can become especially confusing if the application and the AI judge are managed by different teams. The AI judge team might change the judges without informing the application team. As a result, the application team might mistakenly attribute the changes in the evaluation results to changes in the application, rather than the changes in the judges. Do not trust any AI judge if you can't see the model and the prompt used for the judge. AI as a judge. 143. 17. In some cases, evaluation can take up the majority of the budget, even more than response generation. 18. Spot checking is the same as sampling. Evaluation methods take time to standardize. As the field evolves and more guardrails are introduced, I hope that future AI judges will become a lot more standardized and reliable. Increased costs and latency. You can use AI judges to evaluate applications both during experimentation and in production. Many teams use AI judges as guardrails in production to reduce risks, showing users only generated responses deemed good by the AI judge. Using powerful models to evaluate responses can be expensive. If you use GPT-4 to both generate and evaluate responses, you'll do twice as many GPT-4 calls, approximately doubling your API costs. If you have 3 evaluation prompts because you want to evaluate 3 criteria, say, overall response quality, factual consistency, and toxicity, you'll increase your number of API calls 4 times. 17. You can reduce costs by using weaker models as the judges. See what models can act as judges, on page 145. You can also reduce costs with spot checking, evaluating only a subset of responses. 18. Spot checking means you might fail to catch some failures. The larger the percentage of samples you evaluate, the more confidence you will have in your evaluation results, but also the higher the costs. Finding the right balance between cost and confidence might take trial and error. This process is discussed further in Chapter 4. All things considered, AI judges are much cheaper than human evaluators. Implementing AI judges in your production pipeline can add latency. If you evaluate responses before returning them to users, you face a trade-off: reduced risk but increased latency. The added latency might make this option a non-starter for applica tie-ins with strict latency requirements. Biases of AI as a judge. Human evaluators have biases, and so do AI judges. Different AI judges have different biases. This section will discuss some of the common ones. Being aware of your AI judge's biases helps you interpret their scores correctly and even mitigate these biases. AI judges tend to have self-bias, where a model favors its own responses over the responses generated by other models. The same mechanism that helps a model compute the most likely response to generate will also give this response a high score. In 144, Chapter 3, Evaluation Methodology. 19 Saito et al. 2023, found that humans tend to favor longer responses too, but to a much lesser extent. Xing et al. 2023 experiment, GPT-4 favors itself with a 10% higher win rate, while Claude V1 favors itself with a 25% higher win rate. Many AI models have first position bias. An AI judge may favor the first answer in a pairwise comparison or the first in a list of options. This can be mitigated by repeat the same test multiple times with different orderings or with carefully crafted prompts. The position bias of AI is the opposite of that of humans. Humans tend to favor the answer they see last, which is called recency bias. Some AI judges have verbosity bias, favoring lengthier answers, regardless of their quality. Wu and Aji, 2023, found that both GPT-4 and Claude 1 prefer longer responses, 100 words, with factual errors over shorter, correct responses, 50 words. Saito et al. 2023, studied this bias for creative tasks and found that when the length difference is large enough, e.g., one response is twice as long as the other, the judge almost always prefers the longer one. 19 Both Xing et al. 2023, and Saito et al. 2023, however, discovered that GPT-4 is less prone to this bias than GPT-3. 5, suggesting that this bias might go away as models become stronger. On top of all these biases, AI judges have the same limitations as all AI applications, including privacy and IP. If you use a proprietary model as your judge, you'd need to send your data to this model. If the model provider doesn't disclose their training data, you won't know for sure if the judge is commercially safe to use. Despite the limitations of the AI as a judge approach, its many advantages make me believe that its adoption will continue to grow. However, AI judges should be supplemented with exact evaluation methods and/or human evaluation. What models can act as judges? The judge can either be stronger, weaker, or the same as the model being judged. Each scenario has its pros and cons. At first glance, a stronger judge makes sense. Shouldn't the exam grader be more knowledgeable than the exam taker? Not only can stronger models make better judgments, but they can also help improve weaker models by guiding them to generate better responses. You might wonder, if you already have access to the stronger model, why bother using a weaker model to generate responses? The answer is cost and latency. You might not have the budget to use the stronger model to generate all responses, so you use it to evaluate a subset of responses. For example, you may use a cheap in-house model to generate responses and GPT-4 to evaluate 1% of the responses. AI as a judge. 145. 20 This technique is sometimes referred to as self-critique or self-ask. The stronger model also might be too slow for your application. You can use a fast model to generate responses while the stronger, but slower, model does evaluation in the background. If the strong model thinks that the weak model's response is bad, remedy actions might be taken, such as updating the response with that of the strong model. Note that the opposite pattern is also common. You use a strong model to generate responses, with a weak model running in the background to do evaluation. Using the stronger model as a judge leaves us with two challenges. First, the strongest model will be left with no eligible judge. Second, we need an alternative evaluation method to determine which model is the strongest. Using a model to judge itself, self-evaluation or self-critique, sounds like cheating, especially because of self-bias. However, self-evaluation can be great for sanity checks. If a model thinks its own response is incorrect, the model might not be that reliable. Beyond sanity checks, asking a model to evaluate itself can nudge a model to revise and improve its responses. Press et al., 2022, Go et al., 2023, Valmikamat et al., 2023. 20 This example shows what self-evaluation might look like. Prompt, from user, what's 10 plus 3? First response, from AI, 30 Self-critique, from AI, is this answer correct? Final response, from AI, no it's not. The correct answer is 13. One open question is whether the judge can be weaker than the model being judged. Some argue that judging is an easier task than generating. Anyone can have an opinion about whether a song is good, but not everyone can write a song. Weaker models should be able to judge the outputs of stronger models. Xing et al. 2023 found that stronger models are better correlated to human preference, which makes people opt for the strongest models they can afford. However, this experiment was limited to general-purpose judges. One research direction that I'm excited about is small, specialized judges. Specialized judges are trained to make specific judgments, using specific criteria and following specific scoring systems. A small, specialized judge can be more reliable than larger, general-purpose judges for specific judgments. 146, Chapter 3, Evaluation Methodology. 21 The BLERT score range is confusing. It's approximately between -2.5 and 1.0. This highlights the challenge of criteria ambiguity with AI judges. The score range can be arbitrary. Because there are many possible ways to use AI judges, there are many possible specialized AI judges. Here, I'll go over examples of 3 specialized judges: reward models, reference-based judges, and preference models. Reward model: a reward model takes an A, prompt, response, pair and scores how good the response is given the prompt. Reward models have been successfully used in RLHF for many years. CAPI is an example of a reward model developed by Google, 2023. Given a pair of prompt, response, CAPI produces a score between 0 and 1, indicating how correct the response is. CAPI is a lightweight scorer with 360 million parameters, much smaller than general-purpose Foundation models. Reference-based judge: a reference-based judge evaluates the generated response with respect to one or more reference responses. This judge can output a similarity score or a quality score, how good the generated response is compared to the reference responses. For example, BLERT, Selim et al., 2020, takes an A, candidate response, reference response, pair and outputs a similarity score between the candidate and reference response. 21 Prometheus, Kim et al. 2023, takes in, prompt, generated response, reference response, scoring rubric, and outputs a quality score between 1 and 5, assuming that the reference response gets a 5. Preference model: a preference model takes in, prompt, response 1, response 2, as input and outputs which of the two responses is better, preferred by users, for the given prompt. This is perhaps one of the more exciting directions for specialized judges. Being able to predict human preference opens up many possibilities. As discussed in Chapter 2, preference data is essential for aligning AI models to human preference, and it's challenging and expensive to obtain. Having a good human preference predictor can generally make evaluation easier and models safer to use. There have been many initiatives in building preference models, including PandaLM, Wang et al., 2023, and JudgeLM, Zhu et al., 2023. Figure 3.9 shows an example of how PandaLM works. It not only outputs which response is better but also explains its rationale. AI as a judge: 147. 22 such as using a Likert scale. Figure 3.9. An example output of PandaLM, given a human prompt and 2 gen-erat responses. Picture from Wang et al. 2023, modified slightly for readability. The original image is available under the Apache license 2.0. Despite its limitations, the AI as a judge approach is versatile and powerful. Using cheaper models as judges makes it even more useful. Many of my colleagues, who were initially skeptical, have started to rely on it more in production. AI as a judge is exciting, and the next approach we'll discuss is just as intriguing. It's inspired by game design, a fascinating field. Ranking models with comparative evaluation. Often, you evaluate models not because you care about their scores, but because you want to know which model is the best for you. What you want is a ranking of these models. You can rank models using either pointwise evaluation or comparative evaluation. With pointwise evaluation, you evaluate each model independently, 22 then rank them by their scores. For example, if you want to find out which dancer is the best, U148, Chapter 3, Evaluation Methodology. Evaluate each dancer individually, give them a score, then pick the dancer with the highest score. With comparative evaluation, you evaluate models against each other and compute a ranking from comparison results. For the same dancing contest, you can ask all candidates to dance side by side and ask the judges which candidate's dancing they like the most, and pick the dancer preferred by most judges. For responses whose quality is subjective, comparative evaluation is typically easier to do than pointwise evaluation. For example, it's easier to tell which song of the two songs is better than to give each song a concrete score. In AI, comparative evaluation was first used in 2021 by Anthropic to rank different models. It also powers the popular LMSYS's chatbot Arena leaderboard that ranks models using scores computed from pairwise model comparisons from the community. Many model providers use comparative evaluation to evaluate their models in production. Figure 3.10 shows an example of ChatGPT asking its users to compare two outputs side by side. These outputs could be generated by different models, or by the same model with different sampling variables. Figure 3.10. ChatGPT occasionally asks users to compare two outputs side by side. For each request, two or more models are selected to respond. An evaluator, which can be human or AI, picks the winner. Many developers allow for ties to avoid a winner being picked at random when drafts are equally good or bad. Ranking models with comparative evaluation. 149. A very important thing to keep in mind is that not all questions should be answered by preference. Many questions should be answered by correctness instead. Imagine ask ing the model, is there a link between cell phone radiation and brain tumors, and the model presents two options, yes and no, for you to choose from. Preference-based voting can lead to wrong signals that, if used to train your model, can result in misaligned behaviors. Asking users to pick can also cause user frustration. Imagine asking the model a math question because you don't know the answer, and the model gives you two different answers and asks you to pick the one you prefer. If you had known the right answer, you wouldn't have asked the model in the first place. When collecting comparative feedback from users, one challenge is to determine what questions can be determined by preference voting and what shouldn't be. Preference-based voting only works if the voters are knowledgeable in the subject. This approach generally works in applications where AI serves as an intern or assistant, helping users speed up tasks they know how to do, and not where users ask AI to perform tasks they themselves don't know how to do. Comparative evaluation shouldn't be confused with A/B testing. In A/B testing, a user sees the output from one candidate model at a time. In comparative evaluation, a user sees outputs from multiple models at the same time. Each comparison is called a match. This process results in a series of comparisons, as shown in Table 3.5. Table 3.5. Examples of a history of pairwise model comparisons. Match #model A model B winner 1 model 2 model 1 2 model 3 model 10 3 model 7 model 4 model 4. The probability that model A is preferred over model B is the win rate of A over B. We can compute this win rate by looking at all matches between A and B and calculating the percentage in which A wins. If there are only two models, ranking them is straightforward. The model that wins more often ranks higher. The more models there are, the more challenging ranking becomes. Let's say that we have 5 models with the empirical win rates between model pairs, as shown in Table 3.6. It's not obvious, from looking at the data, how these 5 models should be ranked. 150. Chapter 3, Evaluation Methodology. 23. Even though Chatbot Arena stopped using the ELO rating algorithm, its developers, for a while, continued referring to their model ratings ELO scores. They scaled the resulting Bradley-Terry scores to make them look like ELO scores. The scaling is fairly complicated. Each score is multiplied by 400, the scale used in ELO, and added to 1000, the initial ELO score. Then this score is rescaled so that the model Llama 13B has a score of 800. Table 3, 6. Example win rates of 5 models. The AB column denotes the event that A is preferred to be. Model pair # model A model B # matches AB 1 model 2 1090% 2 model 1 model 3 1040% 3 model 1 model 4 1015% 4 model 1 model 5 1010% 5 model 2 model 3 1060% 6 model 2 model 4 1080% 7 model 2 model 5 1080%, 8 model 3 model 4 1070% 9 model 3 model 5 1010% 10 model 4 model 5 1020%. Given comparative signals, a rating algorithm is then used to compute a ranking of models. Typically, this algorithm first computes a score for each model from the comparative signals and then ranks models by their scores. Comparative evaluation is new in AI but has been around for almost a century in other industries. It's especially popular in sports and video games. Many rating algorithms developed for these other domains can be adapted to evaluating AI models, such as ELO, Bradley-Terry, and TrueScale. LMSYS's Chatbot Arena originally used ELO to compute models ranking but later switched to the Bradley-Terry algorithm because they found ELO sensitive to the order of evaluators and prompts. 23A ranking is correct if, for any model pair, the higher-ranked model is more likely to win in a match against the lower-ranked model. If Model A ranks higher than Model B, users should prefer Model A to Model B more than half the time. Through this lens, model ranking is a predictive problem. We compute a ranking from historical match outcomes and use it to predict future match outcomes. Different ranking algorithms can produce different rankings, and there's no ground truth for what the correct ranking is. The quality of a ranking is determined by how good it is in predicting future match outcomes. My analysis of Chatbot Arena's ranking shows that the produced ranking is good, at least for model pairs with sufficient matches. See the book's GitHub repo for the analysis. Ranking models with comparative evaluation, 151. Challenges of comparative evaluation with pointwise evaluation. The heavy lifting part of the process is in designing the benchmark and metrics to gather the right signals. Computing scores to rank models is easy. With comparative evaluation, both signal gathering and model ranking are challenging. This section goes over the 3 common challenges of comparative evaluation. Scalability bottlenecks. Comparative evaluation is data-intensive. The number of model pairs to compare grows quadratically with the number of models. In January 2024, LMSYS evaluated 57 models using 244,000 comparisons. Even though this sounds like a lot of comparisons, this averages only 153 comparisons per model pair. 57 models correspond to 1,596 model pairs. This is a small number, considering the wide range of tasks we want a foundation model to do. Fortunately, we don't always need direct comparisons between 2 models to determine which one is better. Ranking algorithms typically assume transitivity. If Model A ranks higher than B, and B ranks higher than C, then with transitivity, you can infer that A ranks higher than C. This means that if the algorithm is certain that A is better than B and B is better than C, it doesn't need to compare A against C to know that A is better. However, it's unclear if this transitivity assumption holds for AI models. Many papers that analyze ELO for AI evaluation cite transitivity assumption as a limitation. Bugder et al., Balduzzi et al., and Munoz et al. They argued that human preference is not necessarily transitive. In addition, non-transitivity can happen because different model pairs are evaluated by different evaluators and on different prompts. There's also the challenge of evaluating new models. With independent evaluation, only the new model needs to be evaluated. With comparative evaluation, the new model has to be evaluated against existing models, which can change the ranking of existing models. This also makes it hard to evaluate private models. Imagine you've built a model for your company, using internal data. You want to compare this model with public models to decide whether it would be more beneficial to use a public one. If you want to use comparative evaluation for your model, you'll likely have to collect your own comparative signals and create your own leaderboard or pay one of those public leaderboards to run private evaluation for you. 152, Chapter 3, Evaluation Methodology. 24. As Chatbot Arena becomes more popular, attempts to game it have become more common. While no one has admitted to me that they tried to game the ranking, several model developers have told me that they're convinced their competitors tried to game it. The scaling bottleneck can be mitigated with better matching algorithms. So far, we've assumed that models are selected randomly for each match, so all model pairs appear in approximately the same number of matches. However, not all model pairs need to be equally compared. Once we're confident about the outcome of a model pair, we can stop matching them against each other. An efficient matching algorithm should sample matches that reduce the most uncertainty in the overall ranking. Lack of standardization and quality control. One way to collect comparative signals is to crowdsource comparisons to the community the way LMSYS Chatbot Arena does. Anyone can go to the website, enter a prompt, get back 2 responses from 2 anonymous models, and vote for the better one. Only after voting is done are the model names revealed. The benefit of this approach is that it captures a wide range of signals and is relatively difficult to game. 24. However, the downside is that it's hard to enforce standardization and quality control. First, anyone with internet access can use any prompt to evaluate these models, and there's no standard on what should constitute a better response. It might be a lot to expect volunteers to fact-check the responses, so they might unknowingly prefer responses that sound better but are factually incorrect. Some people might prefer polite and moderate responses, while others might prefer responses without a filter. This is both good and bad. It's good because it helps capture human preference in the wild. It's bad because human preference in the wild might not be appropriate for all use cases. For example, if a user asks a model to tell an inappropriate joke and a model refuses, the user might downvote it. However, as an application developer, you might prefer that the model refuses. Some users might even maliciously pick the toxic responses as the preferred ones, polluting the ranking. Second, crowdsourcing comparisons require users to evaluate models outside of their working environments. Without real-world grounding, test prompts might not reflect how these models are being used in the real world. People might just use the first prompts that come to mind and are unlikely to use sophisticated prompting techniques. Ranking models with comparative evaluation, 153. Among 33,000 prompts published by LMSYS Chatbot Arena in 2023, 180 of them are hello and hi, which account for 0.55% of the data, and this doesn't yet count variations like hello, hello, hola, hey, and so on. There are many brain teasers. The question X has 3 sisters, each has a brother. How many brothers does X have, was asked 44 times. Simple prompts are easy to respond to, making it hard to differentiate models' performance. Evaluating models using too many simple prompts can pollute the ranking. If a public leaderboard doesn't support sophisticated context construction, such as augmenting the context with relevant documents retrieved from your internal databases, its ranking won't reflect how well a model might work for your RAG system. The ability to generate good responses is different from the ability to retrieve the most relevant documents. One potential way to enforce standardization is to limit users to a set of predetermined prompts. However, this might impact the leaderboard's ability to capture diverse use cases. LMSYS instead lets users use any prompts, but then filter out hard prompts using their internal model and rank models using only these hard prompts. Another way is to use only evaluators that we can trust. We can train evaluators on the criteria to compare 2 responses or train them to use practical prompts and sophisticated prompting techniques. This is the approach that Scale uses with their private comparative leaderboard. The downside of this approach is that it's expensive and it can severely reduce the number of comparisons we can get. Another option is to incorporate comparative evaluation into your products and let users